Hello, welcome back. As promised, we are going to do space math. I am such a nerd and I absolutely love this stuff. This is one of the favorite lessons that I get to teach you guys all year. There are some other extension activities that I do that are like well beyond just the scope of the course, getting into the real world. That we like to do at the end of the year. I'm going to try to upload those as well. So there'll be even more of this. To talk about Christopher Columbus and other such things like that. I think you guys are going to really enjoy this. So sit back and watch. And oh yeah, by the way, this is the back of your assignment, so we're going to do it together. So lots of lovely graphics we get to look at together. I think you guys are going to love it. All right, so moving along, before we can go to space, we're going to start really low, really low to sea level, actually. So the first question we have is, how far into the ocean can you see if you're standing on a beach? So let's assume that your eyes are 6 feet above the ground, so be a fairly tall girl there. It's the same girl we use for the one flying the kite, in case you're wondering, the silhouette. So if your eyes are 6 feet above the ground, how far can you see into the ocean? Now keep in mind, the world is not flat. I know, trigger warning. The world is actually round. And so the ocean itself is actually a perfectly curved surface. Now I know it's got hills and valleys from the crest and stuff like that, but overall it is perfectly flat if it was completely still. So working on sea level and on flat ground or perfectly straight, because of course it's not flat, it's round. I know, you guys are like, even you don't believe it. Whatever. So it is, it's actually a perfect curved surface here. So we know that the radius of the Earth is 6,400 kilometers. It's actually closer, I think, 6,370 or 83 or something like that, but we'll just use 6,400 for our estimate, so it's close enough. So what we notice here is that this point of tangency, this is the horizon. That's the furthest you can see. So if she's looking along this blue line, the part of the Earth that she sees is any of this purple part. Anything beyond that purple arc here, she won't be able to see because this point of tangency is in the way. So for all extensive purposes, this is the furthest that she can see. Now the world keeps curving out of her vision after that, but this is the farthest distance that she can see. So we want to solve for this blue line here. What's the length that she can see from 6 feet above sea level looking across the ocean? So pretty cool question. Then we're going to move on to the second part, which is if she gets into a lifeguard tower. So made that, I know, not much of a graphic artist, but anyway, she's in this lifeguard tower and her eyes are now 16 feet above the sea level. Now how far can she see? And you can clearly see from, you can see how far can you see? But anyway, you can clearly see she can see further, and that's why they have lifeguard towers, so that they can see further into the ocean. They can see the ships coming from further away, when if you were just on the beach itself, like the girl over here, you wouldn't be able to see that. All right, so how would we solve these problems? So we pose both of these questions. We know we're dealing with the radius of the Earth of 6,400 kilometers. We know how high we are above sea level, and we want to find out what's this blue distance here on both of these. How are we going to solve this? So do you see the triangles? We have two triangles here. What special kind of triangles are they? Well, since we're dealing with tangent lines, which we did the lesson before this one, those are right angles. Tangent lines are going to be perpendicular to the radius that goes through the point of tangency, and with the circle that's formed by that we're talking about to the center of the Earth, right? So if this is a right triangle, what do we know about right triangles? We know the length of this hypotenuse here. We know that the leg here is 6,400 kilometers, and this is just another leg here. So we can solve for the missing leg by using the Pythagorean theorem. Because this is a right triangle, we know a squared plus b squared is equal to c squared. What's kind of cool is that what we're doing so far is just like middle school level math, but it's literally space math. Now we're going to get into a little bit of trig, so geometry level trig, but everything that we've done from our right triangles unit is going to apply to circles here for a moment and to the real world, and I think it's going to blow your mind. You're going to love it. So let's go ahead and solve these values. I'm going to break them down into two separate problems here. So this is number 17 on the back side of your homework. So the first one, I'm just showed a different diagram here, but the radius of the Earth we know is 6,400 kilometers. So that's the radius for both of those. The height above sea level, we're going to set that as 6 feet. And all we want to do is solve for this distance here. We can call that x or d. So when we plug this into the Pythagorean theorem, we're going to end up with 6,400. So this is the hypotenuse. 6,400 plus 6, or our height, squared minus 6,400 squared is going to be equal to the distance squared. So this is just a modified version of the Pythagorean theorem where we subtracted one of the legs from both sides to get it where it's the hypotenuse minus a leg is equal to the leg. That's how we solve for the legs, by using subtraction. Now, the other thing is we can't just do 6,400 plus 6 because these are in different units. We have kilometers and feet. So we're going to have to do a few conversions here. Don't freak out. That's what our calculator is for. So I've also got the conversion values down here. So if we want to go from feet to meters, we have to multiply by that value. So let me go ahead and do that with my calculator real quick. So we want to know what is 6 feet times 0.3048. So that's going to be about 1.8 meters. And so if I'm 6 feet tall, I'm about 1.8 meters tall. So internationally, people ask me my height. I won't tell them that I'm 6'2". I'll tell them about 1.8 meters or 182 centimeters, which is what they would know. All right, so kind of cool. That is exactly what we would expect it to be. So now we want to add those meters to the kilometers. Now, when we do that, we have to be careful the decimal. So we have 6,400.00188288. Now, the reason I had to put this decimal here is because 6,400 is in kilometers, which is 1,000 meters. So if we move the decimal 3 places, that puts this in the meters point. So this is how far away I am from the center of the Earth, which is very minuscule when you look at the actual distance to the center of the Earth. So I'm going to take that value and square it. So that was this part right here, plus my height converted to meters or kilometers, minus, then I'm going to do 6,400, the radius of the Earth. That's going to be one of our legs. I'm going to do that squared. And then just hit enter. And that's going to be the difference between those two. Now, it's not just the difference, it's the square difference. So what I have to do, that's d squared right here, okay? So in order to find what d is, the distance that we can see, all I have to do is take the square root of that value. So to the 1/2 power, which will give me 4.8. Now, that's 4.8 kilometers. So we might want to convert that to miles, which 4.83 kilometers. To change that to miles, just multiply it by the scale factor, which gives us roughly 3 miles. So that's kind of cool. Let me go back to the visual because it's kind of nice to look at. So if your eyes are 6 feet above the ground, which mine are close to, how far can I see into the ocean? Well, I can see a distance of approximately, we just found, 3 miles, which is kind of cool. So if there was a ship out there, now it's a little different because if there's a ship, they're actually higher than that point of tangency. So we could actually see the ship further back. But we won't talk about that until we talk about Christopher Columbus, which will be in a few weeks. Or maybe, yeah, about 3 to 4 weeks. I'll put that out. But it'd be kind of cool. But how far can we see into the ocean? About 3 miles. Now, the real distance we would actually be probably measuring would be the distance along this curve, right? So how far of the distance into the ocean can we see? Not this hypotenuse length here, but the actual, or the leg length, but this length of the curve. Now, when we're talking about such small differences, I can find that length of the curve using our arc length formula, but when we're talking about such small distances here, the difference between those two is pretty much negligible. So we can just kind of ignore that and just do the simple math. But I will show you how to do that when we get into space, because then all of a sudden the difference between those two values is very drastic. Thank the moon. All right, so that was how far we can see, about 3 miles. So how far if we get into a life tower that's 10 feet tall? So now our eyes are 16 feet above the sea level. All right, so that's number 18. We're going to do the same process, except now we're going to use 18 as our h. So I'm going to convert that 18 feet to meters by multiplying it by 0.3048. Okay, so that's about 5.5 meters. And I'm going to add that to 6,400. So 6,400.005, try that again, 54864. All right, now double check, make sure your decimals are right, because this is kilometers, and so there's 1,000 meters in a kilometer. Yeah, so we did it right. I'm going to take that value, I'm going to square it, and then I'm going to subtract it from the radius of the Earth squared, which was our other leg. And that's going to give me the squared difference between the squared distance that I can see. So all I have to do now is take the square root of that value, just like I did in the last problem, which is going to give me the distance I can see from the tower, which is about 8.3 kilometers. Or if I convert that to miles, close to 5 miles. So why do they get up into the tower, the lifeguard tower? Because instead of only being able to see 3 feet, which you can see from the shore, you can now see about, what was it, 5? or sorry, not 3 feet, but 3 miles. Now we can see about 5 miles. So we can almost see twice as far just by getting up into the tower, which is kind of nice. All right, so again, I said we're gonna do space math, but we're gonna crawl before we walk, and then we're gonna run, and it's gonna be awesome. Okay, so the next one, we're gonna go up here. This is called the Lighthouse of Alexandria. It was one of the 7 wonders of the world. They began construction in 290 BC, and you probably are familiar with Alexandria because that's where Euclid is from, the father of geometry. We've talked about him quite a bit. So it was a port island on the Mediterranean coast of Egypt. So really famous. It was the learning capital of the world. They had a university there, and there were a lot of people that studied math and astronomy. A lot of famous people that you probably have heard of that were in Alexandria or studying in Alexandria at some time. So we believe that the Lighthouse of Alexandria has not survived. It's been destroyed because it was very, very old. But from drawings, we believe that it was about 450 feet above sea level. So I've kind of broken down some of the dimensions here. I measured them on my screen with the estimates and then how high above sea level. So we believe it was about 450 feet above sea level. So the claim is they built the Lighthouse of Alexandria. So at night they would have fire at the very top because of course they didn't have electricity back then, like we would use in a lighthouse today. But they would light a fire up at the very top. And at night, you could see that fire. They claimed you could see it from 100 miles away. And that would guide all these ships that you see. It would guide them into the port of Alexandria, which is where they were trying to go. So that was the idea. Now we're going to test that claim. So could you really see that flame at night from 100 miles away? Sounds like a hard question to answer, but we know how to do the math. It's exactly the same thing. It's just a slightly larger number. So instead of saying our height was 6 feet or 16 feet, now we're going to do a height of 450 feet above sea level. So crunch the numbers. Here we go. All right, so we're going to start out with 450, and we're going to multiply that by our scale factor of 0.3048 to change it to meters. And then I want to add that to our kilometers. So make sure I use the right decimals here. So that's actually going to be 137.16. Okay, and notice that if I go 3 decimals over, because it's kilometers again, that's going to give me 137.16 meters. And there are 1,000 meters in a kilometer, so that's exactly what it should be. We're going to take that, then we're going to subtract it by the radius of the Earth squared, which was our other leg. So hypotenuse squared minus leg squared. That's going to give us a squared distance. So all I have to do then, just like I did before, take the square root of that value, which will give me 41.9 kilometers. Okay, now if I change that from kilometers to miles, that's only 26 miles. Now the claim was that you could see at night, you could see the lighthouse from 100 miles away. Now, we just tested that claim, and if it was 400 feet above sea level, that's a bunch of crap. So it's not looking very good for the myth, is it? So 26 miles is nowhere near the 100 miles that was claimed. So let's go back to our picture and try to see what's going on here. So maybe when they made this claim, the light here at night, all we would see would be the light, right? But if it was a fire, you see all the smoke? That smoke's going to rise. And so if that smoke rose higher, you might be able to see the smoke during the day. So maybe the claim was actually that they could see 100 miles during the daytime. So how high would that smoke have to rise? Now, this is a slightly different question, but and we're kind of working a little bit backwards, but it's actually totally possible to solve that value. I'm debating whether or not I show you how to do the math or if I just show you the answer. All right, so let's try this out. So if we want to be able to see 100 miles, that's the distance. That's one of our legs. So we're going to do, okay, yeah. So I'm going to do 64, so it's miles. So I'm going to have to convert it back. So 100 miles, and then I'm going to divide that by 0.6214. Okay, so 100 miles divided by that value. That'll tell me how many kilometers. Now I'm going to add that to 6,400. Or sorry, actually, because that's the distance we want. So I'm just going to square it. Whoa, what just happened there? Let me clear that out. Okay, so I'm going to take this value. I'm going to square it. And I'm going to add it to the other leg, which is 6,400 squared. Okay, that's the other leg. So it's just Pythagorean theorem. A squared plus B squared. So the distance we can see Let me go back to a diagram here. So it's the distance that we can see, which we said was 100 miles squared, but it was 160 kilometers squared, plus 6,400 kilometers squared. And then that's going to give me the distance that I can see in kilometers above what this value is. So I think once I show you the last part, it'll all come together. Where were we? Oops. Shh. We're not going there. Spoilers. Okay, so that's that. And then again, that's the squared hypotenuse. So I'm going to take the square root of that value, which leaves me with 6,402 kilometers. So remember, this is our hypotenuse. The height that we want is actually 2.02. That's the part that's above the actual radius of the Earth, right? That's the h that's being added to the 6,400. So the question is, how far would the smoke have had to have risen? Would have to be 2.02 kilometers, or when I change it to feet, about 6,637 feet. Now keep in mind that light sport aircraft cruise around 10,000 feet, and this is of course over I think roughly 5.8 thousand feet is a mile. I'm probably off on that. Shame on me. But anyway, it is over a mile in the air. So could the smoke have risen over a mile high? Yes. And if the smoke was over a mile high, then we would be able to see the smoke from 100 miles away during the day. But as far as during the night, when all you could see was the flame, 450 feet is far, far less than the amount of feet that it would have to be in order for us to be able to see it from 100 miles away. So we can pretty much bust the claim during the nighttime. They would only be able to see 26 miles. And during the daytime, if the smoke rose 2.02 kilometers or just slightly over a mile into the air above sea level, then we'd be able to see it from 100 miles away. Pretty cool. So we're still not yet to space. We're just at the lighthouse. What about Mount Everest? So it's the highest you might be, or the highest you would be if you were still on land and not flying. So this is number 20. Mount Everest is about 8.85 kilometers, which is nice. Our units are in kilometers. We don't have to do any conversions. So all we have to do is plug this into our calculator. So I'm going to do 6,408.85. Then I'm going to square that. Subtract from that 6,400 squared, which is our other leg. That's going to give us the squared distance in kilometers. And then take the square root of that value, so caret 0.5, which is going to leave us with 336.7 kilometers. So 336.7 kilometers, and if I change that to miles, it's about 209 miles. So if you were at the top of Mount Everest, how far could you see? You could see if the land, of course, is flat, and it's not actually flat, so we can't really. It doesn't quite work out this nice because we're not right next to the ocean, which would be a flat curved surface. So that kind of sounds like an oxymoron, but it's okay. We would potentially be able to see up to 209 miles unobstructed if it was actually indeed a perfectly flat surface. Now we're in the middle of Nepal. We're in Mount Everest, and the Himalayan mountains are much wider than just 209 miles. So that's definitely not going to be the case. But best case scenario, 209 miles. Kind of cool. Let's go to space. All right, the International Space Station, ISS. The International Space Station cruises at an altitude about 350 kilometers above sea level. I'm just going to pause because this is just so cool. We're literally talking about space. So my question that I have is, how far can they see from the International Space Station? And if you think about being in space and how far away from the Earth space is, hint, hint, this is not drawn to scale. So they actually can't see as far as you think that they can. And that's going to be pretty cool when we discover. All right, so what's this distance? Well, if the radius of the Earth is 6,400 kilometers, then think about that with what 350 is with respect to that. It's going to be about, I believe, 5% of that length. So if we actually mark this to scale, it's only going to be about this high above the Earth, about right there. So if the International Space Station is about right there, how much of the Earth can they see? Well, this is obviously not to scale. They can actually only see a small window or small field of view because they're so close to the surface. They're orbiting really, really fast, right above the Earth, right? Going really fast so they don't fall into the Earth, right? That's how orbit works. Talk to your physics teacher. Wonderful course, by the way. And so they can actually only see very small field of view. So how do we calculate that exact field of view? Well, the math is exactly the same as it was before. Now that we're in space, it kind of makes things a little bit easier. We can kind of neglect the surface of the Earth not being like perfectly round and flat. Perfectly flat and round. Oxymoron. The world's not flat. Okay, for the millionth time. Also, don't eat Tide Pods. They will kill you. You're welcome. It's a public service announcement. So all we're going to do, this again is already in kilometers, so it makes our math pretty easy. So 6,400 plus 350 would be 6,750. We're going to square that. I'm going to subtract that from 6,400 squared. That's going to give us our distance squared. Ooh, yeah, that's what we call a typo. What's nice about the math print is that I can actually go back and just edit those. And we're good. We're back to where we started. Okay, so that's going to be the square distance. So all I have to do again is take the square root of that to find the length of our leg, which is about 2,145 kilometers. Now, if I change that value from kilometers to miles, it'll tell me they can see about, I didn't do it, but you can do it. I think it's like 300 miles or something like that. Okay, fine. I'll do it. I'll go back to my conversion factors. Okay, kilometers to miles. Okay, so we're going to take this value, we're going to multiply it by 0.6214, which is, about 1,300 miles. So what is that width? 1,300 miles. Well, it's kind of cool. So I looked it up on Google Maps, and that is about twice the width of Texas, or about the size of the Gulf of Mexico. So when they're orbiting this close to the Earth, 350 kilometers, they can only see about twice the width of Texas, or about the Gulf of Mexico. So let me show you an actual picture from the International Space Station, just to kind of show what's really going on here. I know these graphics are like killer. All right, so this is the International Space Station, a photo from the International Space Station. They're orbiting 300 kilometers above the Earth, and they can see about 20.6% of half of the world, because of course we can't see the back half, but we'll get to that in a bit. Do you recognize what they're looking at right there? You probably know it. It's a country that looks like a boot, right? Okay. Yep, you got it. Okay, so thank you for screaming at your phone, and I can definitely hear you through the phone, so keep doing that. We're going to pretend like we're still in the classroom together. I know, this is so sad. I really do miss you guys, but I'm not going to get into that because I'll start crying. So we're trying to make the best of this distance learning thing. At least I get to share all the cool stuff with you, which is, it's a light at the end of the tunnel. Okay, so here we have, this is Italy, right? And from Italy, how much of Europe can you really see? Maybe over here we can start to see into France or Germany, but I'm not sure if we could actually see the Netherlands from here. It's actually in the horizon, right? So the Netherlands is on the other side of the tangent line, right? The horizon. So we can't actually see that far. How far over here can we see into to Southeast Europe? Not that far, really. I'd be surprised if we can see Greece, maybe, but maybe not on the other side of the Aegean Sea. We definitely, I can't see the Aegean Sea back there or anything like that. So, I love geography, by the way. So yes, Italy, twice the width of Texas. All they can see is about twice the width of Texas or the Gulf of Mexico at any given time. Now, of course, they're going really fast, so they're not going to be looking at Italy for very long, I believe, because keep in mind, they're orbiting really fast, really close to the surface. And because they're so close, they have to orbit really, really fast. I'm not sure what their orbit time is, but that'd be kind of cool. So for a while there, they're just looking at the ocean, like the Pacific Ocean, and all they can see is ocean, 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 and then boom. Yeah. It's kind of cool. Then they can finally see land again. All right. So here's another photo from the International Space Station. This is also, I believe, Italy. Yeah, you can see that this is definitely Italy. There's a lot of clouds, so it's kind of hard to see any other land features, but we definitely have northern Italy here. So we have Switzerland just right above it, and we're also kind of in a different place. We could see further down south in this photo. But anyway, again, another photo from the International Space Station. Cool stuff. All right, so the next question is, if we could see about 20% of the world from the International Space Station, which is this little blue mark here, kind of did some rough estimates, then how far would we have to back up or go further out into space in order to see half of the world, from like the top to the equator. So from the North Pole to the equator, that would be 50% of half of the Earth, right? So 50% of one side of the world. How far would we have to go back? Now, this question is actually really simple to answer, and that's because if we look at this is a square, right? And so if we have a square, we want to know if we extended this side here, that's the radius, so radius of 1, and we go over to here. This is a special right triangle, right? That's a 1, 1 radical 2, an isosceles right triangle. And so we can find the difference between those two fairly simply by just looking at a scale factor. And this is fascinating because it's just simple right triangle math that we already know, but we're applying it to literally the world. So what's our scale factor for going from 1 to 6,400? Well, that's a scale factor of the entire radius of the Earth, right? Which is pretty stinking awesome. So anyway, so that's just going to be times 6,400. So what does this one turn into? 6,400. And the radical 2, well, 6,400 radical 2 kilometers, right? So if I just want to know the height above there, not the distance from the center of the Earth, but the distance above sea level, which is how we would measure the height or the elevation of the International Space Station, all we would have to do is actually take radical 2 minus 1 and multiply it by our scale factor, because that'll give us this green part right here. So second square root of 2, I'm going to arrow over so I'm no longer in the radical, minus 1. Okay, so that's our scaled down model difference between that. And then just simply multiply it by our scale factor of the entire radius of the world in kilometers. And that gives us the height above sea level they would have to be, which would be 2650 kilometers. So keep in mind, they're only at 350 kilometers. They would have to back up and slow down, of course, to about 2,651 kilometers in order to be able to see the North Pole and the equator at the exact same time. Now, how cool is this math? And we're only getting started. Oh my gosh. Okay, so my brain just keeps going. And so what's further out than the space station? Well, of course, the moon. So the next question I want to answer is, how much of half of the Earth can we see from the moon? So we've seen some photos from space, and it appears that we can see the northern and the southern hemisphere at the same time. So where were those photos taken from? If we didn't go to the moon, just kidding. So of course, they were taken from the moon. And so we actually have photos from the moon, and we can prove that they were actually from the moon by how much of the Earth we can see. Because if we weren't that far away from the Earth, we never would have been able to see the northern and the southern hemisphere at the same time. Crickets. Does anyone else hear crickets to the argument that the world's still flat? It's okay. So I love space. This is so fun. All right. So keep in mind, this is not to scale. So the radius of the Earth is 6,400 kilometers. The radius of the moon is much smaller. So I did put the moon to scale with the Earth, but the distance between those two, this number here, is about a tenth of what the distance actually should be. So if I made this to scale, I would have to take the moon and stretch it 10 times as far away as this distance, and then it wouldn't fit on my board. I have to scale everything down, so it's not exactly to scale. Just keep in mind the moon is really, really, really far away. And we were only 350 kilometers away when we were at the International Space Station. Remember, that's like right there. So that's why it takes such a long time to get to the moon, even though they're hauling donkey postulates. Yeah, I'll leave that in there. So the question we have is, we want to be able to solve for what is this theta? So what percent of the world can we see from the moon? Now, this is just a right triangle. We have our hypotenuse here, which is the distance between the moon and the Earth, plus the radius of the Earth, right, squared. And then we're going to subtract 6,400 squared, and that's going to give us this distance here. Now, we could do that, but that's not actually the distance of the Earth we're seeing. Remember when we talked about the difference between the curvature on the Earth and the actual linear, like straight distance that we could see? When we're really close, it doesn't actually matter. We can neglect the difference, like at the beach. But when we're this far away, that's totally going to be different. So what we really want to know is this theta. How are we going to solve for this theta? Well, we have a leg, and we have a hypotenuse. We don't actually need to solve for the other leg. Remember, if this is a right triangle because it's a tangent line, we can use one of our trig functions, and you're already looking on the page and you already know which one it is, but what trig function can we use? We have the adjacent leg and the hypotenuse, which is cosine. Remember SOHCAHTOA? So cosine is the adjacent over the hypotenuse. So we can set up a cosine function, and we'll do the inverse because we're looking for the angle, right? So inverse cosine of 6,400 divided by this value plus the radius of the Earth. So put that together. Whenever I put that in my calculator, just to speed things up, because I know you know how to do that, we get about 89.06 degrees. Now, this is not the percent of half the world. This is the angle. Now, if we're talking about half the world, we also have to double this, right? Because we can see that on both sides of this. So when I double it, I get 178.12. And then when I divide that by 180 degrees, which would be the semicircle, which is the maximum amount that we could see of the Earth without using mirrors, even though that'd be really cool. We should put mirrors in space so we can see the back half. Oh, wait, that's called satellites. So when we divide those two, we get 98.96%. So how much of the half of the Earth can we see from the moon? Almost all of it, practically all of half of it. There's only slightly some that we can't see. And remember, if I actually drew this to scale, it'd be 10 times as far away. And so these lines would be approaching almost what we would think would be parallel, but they're not. And so, in fact, we'll never actually be able to see exactly half of the Earth. Even if we back away as far as to the sun, we're still going to be approaching exactly half, but we'll never actually see it. But, you know, that's a different argument altogether. So, from the moon, this is a photo from the moon, as far as I'm concerned, if we ever really went there. So this is a photo from the moon or Photoshop. You know, it gets hard to tell these days, where we can see 98.96%. And if you look at this one, should we be able to see the North Pole and the South Pole if we extend down there? Yes, I think so. Can we see the Northern Hemisphere and the Southern Hemisphere at the same time? Yes. So this obviously was not Photoshopped from a photo from the International Space Station, right? This photo would have had to have been taken from much, much further out. And that's the next question we have, because it gets even cooler. All right, so anyway, that's the distance we are from the Earth. That's the percent of the Earth that we can see from the moon. All right, so this is the last one. I'm pretty sure this is the last one I have for you, and it is so cool. So during the Apollo 17 mission where we went to the moon, you couldn't see me, but I did, scare quotes on that, went to the moon. In Apollo 17, they turned around and they took this photo. Of course, it's a long distance, as we've discussed, to get there, and so they had a lot of time, and they took a photo of the Earth. Now, this is a famous photo. You can see the number here for the reference number of a very famous photo. It's also called the Blue Marble. And if you look in it, you can clearly see all the way from Egypt to South Africa, right? And we know from Google Maps the distance between Egypt to South Africa, or the basically the change in the vertical distance in Africa, is about 8,000 kilometers. So from this, my question is, what is our field of view? So how much further could I see to the north and all the way to the south? Obviously, we can see, much further past the South Pole here in Antarctica, because, the whole thing is tilted. But my question is, what is our actual field of view? So how much does this take up of that? So I took an estimate. I think it's going to be a little bit more than twice the width of Africa, or the length of Africa here. So I'm estimating our field of view from the very far north, which would probably be somewhere in maybe Central Europe, to the opposite side almost of Antarctica, to be an estimated distance of about 1,800 or 18,000 kilometers. So that's just my estimate of the field of view from the photo called the Blue Marble. All right, so from that, what can we tell? So this is where it gets pretty cool. Wait, this whole thing has been cool. What am I talking about? So 18,000 kilometers is going to be our field of view. So from the very top part, which we said was like Central Europe, to the very other side almost of Antarctica, is about 18,000 kilometers. We're estimating that's our field of view, right? So the question I have is what would this theta be? What would half of that arc be to get this theta? And once I know that theta, I can use a trig function in order to find out and place where I think the distance is above the Earth. Yeah, that's where we're going with this. So first thing is, I want to find out what fraction or what percent of the 360 degrees is 18,000 kilometers. So to do that, I want to do 18,000 kilometers divided by the circumference of the world. Now to find the circumference of the world, that's going to be 2 pi r. Now we know what r is because that's the radius of the Earth. So 2 pi times 6,400, which is going to give us, I'm going to change that to a decimal. So that's going to be the circumference of the Earth. And then all I have to do is do 18,000 divided by that previous answer. So second ANS, and that'll give me this fraction here. So all I did was I multiplied this. Now all I have to do is multiply that fraction by 360 degrees, and that'll tell me my angle. So that times 360, because that's what is in the whole, which is 161 point something. Okay, so 161.2 degrees, that's what this angle is here. So the angle here is going to be half of that, which is just simply 80.6 degrees roughly. All right, so now that I know this value here is 80.6 degrees, and I didn't put it there, but you see it's color coded. The next question I have is, how am I going to find out what is the distance above sea level? So again, just like last time, I know this is a right triangle. I've got my adjacent side and the hypotenuse, so I set up a trig function. And in this case, I'm going to use the cosine of our angle, which you said was 80.6, is equal to the adjacent side divided by the hypotenuse. So at this point, we know this is equal to a ratio, and so we can solve. We would need to add this or multiply 6,400 plus x to both sides and then do some math. I'm just going to skip all that and just get you straight to the answer. So on this one, our estimate for the distance above sea level for the Apollo 17 mission, when they turned around and took the photo of the blue marble, was 32,785 kilometers. Now, what's cool is we know what the actual distance was. We know what their location was. Apparently, had their geotag on whenever they took the photo. And so the actual estimate was 29,000 kilometers above sea level, which we got really, really, really close to using our estimate from the field of view, which is absolutely incredible. So this here just shows you some quick numbers of how close were we to our estimate. So in blue, that's our estimate field of view angle, half the field of view angle, and their estimate of field of view in kilometers squared. And these are the actual numbers. Now, those are really, really close to each other. Like we probably couldn't have gotten closer just from, just a simple estimate methods that we used. But anyway, whenever we put all that together, that is just absolutely super impressive. So the whole point that I'm trying to make here is that the basic stuff that we learned in middle school about the Pythagorean theorem, and then extending on to right triangle geometry at even just a high school level with cosine and inverse cosine, using our trig functions, has allowed us to not just work with things that work in small scale, and we've seen that many times, but also to apply something to the big scale, like literally space. And it's the same numbers, and as long as we have a calculator to deal with some of those, nasty numbers that pop up, we know the process and we know how to do these things. And if we apply the right triangle geometry to the world around us, like especially with physics, there's no end to the cool stuff that we can actually do. And I hope you guys were inspired by all of this. And the other takeaway is, of course, is that if you're ever traveling in space, just turn around, take a selfie with the Earth in the background, send it to me, and I'll use the field of view from my estimate to calculate exactly or roughly how far away or you are from the Earth or above sea level, like we did with the photo of the blue marble. So really cool stuff. I'm going to leave you with this graphic in closing. So from the International Space Station, we are only 350 kilometers above sea level, and we can see about 20.6% of the Earth. From the Apollo 17, the blue marble photo, that was 29,000 kilometers, which they could see. I did the math. I didn't show it to you, but you know how it works, right? 88.4% of half of the world. Now from the moon, when we back up from, they were only 29 kilometers compared to the total distance they had to travel. They were very, very early in their trip, but when they took that photo, but they still didn't have to go that far out to see 88%. So, law of diminishing returns kind of at working there. So the moon here, from the moon, we can see almost all of, basically 99% of half of the world. So we'd have to back up even further to be able to see more than that. But even if we went all the way to the sun, kind of think of limits and calculus here, even if we went all the way to the sun, we would still never be able to, at least from one location at a time, which is as much as any person can hope to be in, at least at this point, we can only hope to see up to 99.99%, but it will never, ever, ever get to 100% of half, at least for any human, without using mirrors, because it would be really cool just to put a mirror in the back, then we can see the back, which is what satellites are. So I hope you guys enjoyed that. I'm looking forward to showing this video to some of my friends, because I've talked to people about this, and I've shown it to my students in the past few years, but I don't think I've actually like put it out there. So I think you guys are going to really enjoy this, and I'll be giving you some more extension activities like this, applying to the real world. Maybe not as epic as space math, but I think you guys will be inspired, and hopefully you'll love math as much as I do.